welcome back to Tech Talk with Ray and Mike. And Ray, I'm excited about today's show.
Yeah, it's going to be fun, isn't it?
Oh my goodness.
This is some weird stuff.
Yes, weird, cool, nerdy stuff.
Yeah, this is nerd talk.
So
this
a couple,
nerd talk.
Yeah, definitely. So a couple of podcasts ago, we were talking about the movie Interstellar.
Yeah, right.
And I brought up, well, maybe we should talk about, time and time continuum stuff. And lo and behold, here we are.
Yeah.
Talking time continuum, and can I actually become younger than my daughter?
So the father becomes younger than the daughter.
Right.
That was the premise of the movie, right?
Right.
Why don't you go through the basic plot there?
Okay. Well, if you haven't seen the movie and you don't want to know about it, turn down the volume for a couple seconds and then turn it back up, because spoiler alert. So Interstellar, I'm not a big fan of Matthew McConaughey, first off.
Okay.
I don't think he's a good actor. However,
I liked him.
he was good in this movie.
He was good, yeah.
So this guy, Matthew's a character. He's an astronaut. Earth is turning into a huge dust bowl.
Yep.
And so the world government is sending these astronauts into different galaxies looking for habitable galaxies so we can take everyone on Earth, all billion of us, to a new home.
Yeah.
Right? So the whole thing is the daughter doesn't want the dad to go. The dad says, I have to save the world. He goes, and throughout the course of things, they get stuck on this planet that every hour is like 50...
seven
years.
years. Right, yeah, that's what
Earth.
it was.
And so they get stranded for a long time on this water planet, right?
Yeah.
And by the time he gets home, when all is said and done, she's like 90.
Yeah.
His daughter's 90, and he's still like 30.
Right.
So
she aged and he didn't.
Yeah. So apparently, there's the physicists of the world when this movie was being made, they were totally pumped up because finally Hollywood is going to use actual physics to make a movie and to accurately represent the time continuum and time travel.
But they had to be laughing. I mean,
and much to their disappointment, that's not what they got.
Yeah.
However, I think there might be some fact in there. A little bit.
Yes, right. There's a thread.
There's a thread. There's a thread of truth in everything, right? So that's what we're going to talk about today.
Yeah, so can you get younger than your own daughter?
Yes. Why does going into space, first of all, make me younger?
Okay.
Why didn't it make, younger?
So, well, not only does it make you younger, but it also makes you a time traveler, which we saw in the Interstellar movie. He comes back,
right,
70-some years later, into the future, and so it sort of makes you a time traveler as well. It's interesting to point out that it's not just going into space that makes you younger or makes someone else age where you don't, but there are two reasons for possible time dilation, which they refer to it as. Actually, it's not from the movie. That's an Einstein theory called time dilation, where you're basically causing time to expand or become larger. Think of going into the eye doctor. They put some drops in your eyes, and your eyes dilate, right? It becomes bigger, right? Mm-hmm. Time is not a constant. It is not the same. Time can change, but it always slows down. And so there's two reasons for that. One is traveling very fast. The other is experiencing extreme gravitational pull. And so the movie kind of goes into both of those, but I think they really hit the extreme gravitational pull thing the hardest. They end up losing a bunch of time, and that's the reason the daughter ages and the son doesn't. But this all goes into the relativity of time relative to an observer. So you have an observer who's the daughter on Earth observing, although she can't physically see the sun traveling around the universe, but she is the observer. Everything is relative to her. And so you have her basically observing his time change. And So the fact is, the speed of light never changes. It is a constant. It is the constant. So time is the one that has to change. So let me give you just a kind of an example of how this might work.
Because I'm confused already.
You still don't have an answer yet. Okay. So the short answer, all right, is the faster you go, the farther light has to travel to reach an observer. Okay. So the observer is the daughter on Earth, and the sun is speeding around in spaceships, going fast. And the faster you go, the farther light has to travel to reach that person. Okay. So every observer watching a speeding object observes clocks going slower. Okay. So let's take an example. I'm going to try to give you a little visual here.
Please do.
So you're standing on a platform, a train platform, subway. Okay.
Okay.
Not a lot of people ride subways. Not in the Midwest.
Yeah, not here.
But
yeah,
in the East, big cities, you ride subways.
they're everywhere.
Okay. So you get out on the platform and you're standing there, and there's a train, open doors, and there's a guy standing there. He's 10 feet away. He's got a ball in his hand. See my racquetball here?
I see your racquetball. And by the way, this is also a video podcast. So
yes.
If you want to see his visual.
Yeah, so you can go look at the video on this. So
right.
I've got a ball, okay? I'm standing inside the train car, and there's somebody watching me, okay? So I'm watching this guy, and he holds the ball 3 feet, a meter above the floor and drops it, okay?
Right.
So if you took a piece of paper, a very large piece of paper, and you took a pen and you drew what you saw, just what you observed, as he dropped it, you would see the ball drop vertically.
Right.
It would go straight down.
Right.
Turns out it takes about 450 milliseconds on Earth with our gravitational pull to drop a ball 1 meter.
Okay.
Okay? So you simply see the ball drop. Now, what if the train is moving really fast? I'm going to go with 240 miles an hour. Turns out the fastest train, I think, is like only 230 miles an hour. Fastest train on Earth. Trains used to be the fastest thing on Earth. Well, they're not anymore.
One of the slower things now.
Right. I mean, it's routine to hop on a plane and go 500 miles an hour. I mean, you got jets that go 4,000 miles an hour.
That's insane.
Trains still go pretty fast. So let's say your train is moving 240 miles an hour, and just as the guy comes adjacent to you on the platform, you look through the window and you see him drop the ball.
Right.
I want you to do the same thing. In your mind, take a large piece of paper and just draw what you see. Not the man, but the ball itself, the travel of the ball. Okay?
Okay.
As you're observing, the ball doesn't drop straight down, right? Because the train is speeding along down the track.
Right.
You're drawing a diagonal line because it starts up here, and as it's falling until it reaches the floor, the train is speeding down the tracks, and you finally, observe it hitting the floor. Right. That's a long diagonal line. Right. Turns out at 240 miles an hour, the train is traveling 352 feet per second. Okay?
Okay.
And so at 450 milliseconds, a millisecond is just a thousandth of a second. So 450 milliseconds is 0.45 seconds. So if the ball is dropped 1 meter, the train will travel 158 feet during that time. So you see the guy drop the ball, 158 feet later, the train is way down the tracks. It finally hits the floor. That's a long diagonal line. That's not straight down. So the fact is, light had to travel from the ball to your eye for you to see it.
Right.
So the light had to travel a farther distance. it wasn't that nice, straight, vertical drop. It was 158 feet away. Well, you think, well, light is instantaneous. No, light is not instantaneous, rather slow.
Right.
Turns out light only travels at 186,000 miles per second. It's about 1 foot per nanosecond. If you're working in, microelectronics terms, a nanosecond is an eternity. That's a billionth of a second, by the way. But when you're working with electronics, microprocessors, a nanosecond is like, oh gosh, that is so stinking slow. So it turns out that light only travels a foot in a nanosecond. Okay?
Okay.
So it's kind of slow. Turns out that light, if goes around the Earth, if you were to make it go around the Earth 7.5 times, it would take an entire second to go 7.5 times around the Earth. That's kind of slow. It travels 93 million miles from the sun. Guess how long? It takes 8 minutes and 20 seconds to travel that long. And 1 mile actually takes about 5.5 milliseconds. A millisecond is a millionth of a second. That's really slow in terms of electronics, microelectronics, microprocessors. A millisecond is like forever. And you can execute a huge number of floating point operations in a millisecond.
Really?
So, traveling a mile in 5.4 milliseconds, that's kind of slow. The fact is, if the train has traveled 158 feet down the tracks, it takes a while for that light to reach your eye. Now, you don't notice it because you just don't perceive it.
Right.
But the fact is, it took a long time. So, what I want to establish in your mind is that things that travel fast, clocks on things that travel fast slow down because it takes light longer to travel the distances. Okay?
Okay.
So imagine you're in a spaceship now. Spaceship travels 24,000 miles an hour. Okay? The reason I picked 240 miles an hour is because it's a nice, easy 100 times less than the spaceship, right? So the spaceship's going 24,000 miles an hour. Goodness. Whereas your train is going only 240, because that's a factor of 100. So everything I just gave you, multiply it by 100. If you drop the ball, of course you have no gravity up there, but pretend you did. You drop the ball, same gravity as here on Earth. The spaceship now has moved 15,800 feet, which turns out to be about 3 miles. So
you're looking at almost a vertical line there.
Well,
almost
a horizontal line. Yeah,
I'm sorry,
it's
horizontal.
Very long, long.
Yeah, long line.
Diagonal line, which is nearly vertical. But the fact is, light has to travel all that ways to reach the observer. It's all relative to the observer. That's where this whole theory of relativity comes from. You have an observer. The daughter on Earth is the observer. And so it takes light a lot longer when you're traveling faster. Now, 24,000 miles per hour is actually very slow compared to the speed of light. I mean, it is a thousandth of a percent. I don't know what it is, but it's a very small amount.
Okay.
So you're really not losing that much time. In fact, space travelers who go into space, they do lose a little bit of time. I can kind of go into some of that later, but it is a very, very small amount of time. So the interstellar thing, I don't think they lost a lot of time in their travels at high speed. Okay, I think it came from the other factors which they go into in the movie. So that's but that's kind of an overview as to why time dilation occurs at high speed, and you have to get very, very fast to really make a big difference.
Now, have they proven this?
Absolutely, yes.
And how have they?
What they did was, and it's been proven many, many times, they take an atomic clock.
Okay, what's an atomic clock?
An atomic clock is a device that simply measures the vibrations of a certain type of atom.
Okay.
And there are certain atoms that are very stable, and you can measure the changes in the vibrations of the electrons, and you can get a very accurate reading, ticking of your clock The latest one from NIST, I think, is about 9 billion times per second. We could do another show on that, basically. But an atomic clock is a very, very accurate clock. And the NIST F2 is accurate to within 1 second every 300 million years. Okay, so very accurate. Wow. So you take two atomic clocks, twins, okay, and you put one in an airplane and you fly it around the Earth. So it turns out that the one that you fly around the Earth will lose 273 nanoseconds. So a nanosecond is a billionth of a second. You lose 273 billionths of a second just because you're flying around the Earth at 600-700 miles an hour. So, so just the speed itself makes you lose some time. Now, we're talking nanoseconds here, so billionths of a second.
Right.
So I don't think the movie really works that angle too deeply. I think they go into the other form of time dilation, which is the gravitational time dilation.
Okay. Wow. This is mind-blowing. What really blows my mind is that it's been proven. I mean, not on the scale of Interstellar, but it's
not just a weird mind game. It's an actual fact that when you go fast, light takes longer to travel, and your clocks slow down.
I just keep flying, I just won't grow old.
Right? No, you actually have to fly very, very fast.
Right.
So you will still grow old, but you'll be a few nanoseconds younger.
Dude, that's worth the billions of dollars I can go, put into flying my own aircraft. Okay, so the movie goes into more of the gravitational pull of losing time or of gaining time. See, I'm already confused.
Yeah, the time is always lost. So the time always slows down for the traveler.
Down. Okay. So how does gravitational pull change time? Okay,
so the short answer there. So basically what we're saying here is that there are two ways to change time. One is the light time dilation. The other is gravitational time dilation. Okay. And so when you have a large body of mass with high gravitational pull, like the Earth, the Moon, Mars, Jupiter, they're very dense mass. They have high gravitational pull. It turns out that it takes more time for light to escape that gravitational pull. Not a lot, but depending on the pull, it will take more and more time. So in the movie, they set up a really intense situation where these planets they're encountering have extreme gravitational pull, way beyond what you could ever imagine. But think about black hole. Okay, that's a really good example. Everyone knows about black hole.
Right.
They are so dense. The gravitation is so intense that even light cannot escape. That is how strong their gravitational pull is.
Right.
And so they are slowing light down or they're not slowing light down. Actually, light does not slow down. It is constant. It is always the same speed, but it cannot escape the gravitational pull. But the stronger the gravitational pull, the longer it takes light to escape that pull. So this has also been proven, and what they've done is taken atomic clocks. You take them up onto a mountaintop. You put one at the Dead Sea, and the closer you are to the center of the Earth, the faster the clock will go. So
explain to people why the Dead Sea.
Well, the Dead Sea is the lowest point on the Earth. Okay. So Mount Everest would be the highest point on Earth, and so those you're going to see a difference in those clocks because of the gravitational pull. The one that's closest to the Earth is going to run the slowest. Okay.
Okay.
So again, it's all because light takes longer to escape. And so in the movie, they are basically just, I think they get marooned on this planet that has extreme gravitational pull.
The water planet.
The water planet. They get marooned there. They say every hour we spend here is 7 hours on Earth. They end up losing 23 years there. Okay, and then they escape that, and then they have to go to some other planet and
lose time there.
They end up having to, in order to get to it, they have to slingshot around this other giant, I think the planet called Gargantuan or something like that. It's a slingshot around that.
Right.
And that thing has huge gravitational pull. They end up losing like 51 years there. So the 23 plus the 51, they end up losing 74 years. The daughter is like 90-some. She's nearly on her deathbed. And then the son comes back. He's like 30 years old.
Right.
So
you're mentioning slingshotting. Explain to us what slingshotting is.
Right. Okay. So basically, if you're in a spacecraft, there's a way for you to gain speed. You can use your fuel if you want to, and use your rockets, and you shoot out, burn some of your fuel, and you'll go faster. But there's another way to do it, and that is to get close to a large body, a planet, moon, that has high gravitational force. So you get two boosts of speed from that. First of all, that planet, that moon, whatever it happens to be, is moving at a certain rate of speed relative to our sun. Okay?
Okay.
So let's say you take the moon, for example. It's driving around the Earth, which basically is going around the sun as well. It has a certain velocity, a certain speed relative to our sun.
Right.
Get into its orbit, you are now going at that velocity. Okay. So all you have to do is slip into that orbit, and you're gaining some speed just by the fact that you're now going the same speed as the moon is compared to the sun. So that's one way to get some speed. So what you do is you dip down into the orbit of one of these planets, and it will suck you in because of the gravitational pull.
Okay.
And then it will spit you out if you take a partial revolution around that planet. So you can basically kind of skim in close, use some of that gravitational pull to suck you in, and then it'll spit you back out. So you've gained two bits of speed there. One is relative to the speed of the sun, where that planet has a certain velocity, and the gravitational pull where it actually pulled you in. So they do this to conserve fuel.
Okay,
so,
and NASA's actually done this before.
Oh, yeah, you do it at the moon. The Apollo flights all did it. So, yeah, this was...
it was a common practice.
Yes, yeah, absolutely. You couldn't carry enough fuel. So you have to use these slingshotting methods in order to just make it. And that's how you go long distances in space for free. Because you get to use someone else's gravity to slingshot you, pull you around,
and send you home
without using your own fuel. You don't have to bring rocket fuel to go places. You can just get into somebody's orbit and go. So that's kind of what they did, and they lost 51 years because that gargantuan planet had such huge gravitational pull that they experienced this gravitational time dilation. That's what's going on there in the movie. So I think it's a little far-fetched. All right,
it's Hollywood.
Because those gravitational pulls would be so huge that it would just pin you down. First of all, you couldn't walk on that planet. You'd be smashed to an atom's width,
Right.
You would just be smashed. So I think getting that close to this gargantuan planet, I'm not sure. First of all, it's a very dangerous maneuver, but if you could... I don't know if you would experience that much time dilation or not. I really don't know. I think it may have been a little bit of a stretch.
Maybe just. I mean, I don't. I've never known Hollywood to lead us astray.
Sure. Right.
So,
right. They're always very accurate.
Always. I mean, look at Star Wars, right? We have lightsabers and stuff.
Right, sure.
And speaking of light, what would happen if I traveled at the speed of light?
Okay. Well, first of all, you can't. If you have any mass at all, you cannot reach the speed of light. It would take infinite energy to get you up to that speed, and so you can't do it. In fact, you cannot really, even with today's practical technology, get even close. You cannot even, 24,000 miles an hour is nothing close to 186,000. I mean, it's just, you're just not even getting close.
Right. So probably the closest we can get is speed of sound.
Well, you can break that.
Well, break that.
Yeah,
but
easily
not
break that.
But not much past that, right?
Well,
in the grand scheme of things.
I have to go through the calculations there. Sound travels at 1,100 feet per second. So we're breaking that pretty well if you're going 24,000 miles an hour
right.
many times over. But you're not getting close to the speed of light. But if you could, let's say theoretically you could, first of all, you would burn an infinite amount of energy doing that. Photons actually travel at the speed of light because they have no mass. But if you have mass, it takes the energy then to accelerate you up to that speed, and you just can't do it. But photons have no mass, so they can travel at the speed of light. But if you did actually travel at the speed of light, time would have no meaning. It would basically be just a non-entity.
Okay.
But as you approach the speed of light, time does slow almost to a stop then. As you get right up to it, it becomes infinitely slow. And there's no such thing as infinitely slow, but you get very, very slow. And so time basically stops. Time becomes meaningless. The beginning of your journey is the same as your end of your journey. It is just a meaningless thing. Time does not exist at the speed of light. So, I guess if you could reach the speed of light, time would stop.
So does that mean...
Or cease to exist.
Cease to exist? Does that mean I can go, time travel? Can I go back in time?
No. You can only go forward in time. There is no such thing as going back in time. Does not exist. I mean, it's fun to talk about time traveler.
Back to the Future.
Right, yeah, all that kind of stuff. It's fun.
They did have the speed thing going in Back to the Future, I guess, with the DeLorean and the flux capacitor and stuff.
Sure.
But that's about it, huh?
Yeah, so you can only travel forward in time, as we've talked about, using these two methods, going close to the speed of light or using a very strong gravitational pull. You cannot go back in time. In fact, people have already traveled forward in time. Astronauts do it all the time. And in fact, the Russian cosmonaut Sergei Krikalev, which I've probably butchered his name.
And that's fine. I think half the world does.
has beat the previous record of 20 milliseconds. Okay, so he's traveled into the future 20 milliseconds. Okay, so a millisecond is a thousandth of a second, so 20 thousandths of a second into the future.
Wow.
So not observable to the human observer in our sense of time, but yeah, there you go. He's traveled into the future.
20 milliseconds younger than he was 20 seconds.
Right. Yeah, you got older. Ago. You got 20 milliseconds older. And so he's a young man.
Yeah. He's a young whippersnapper.
Yeah, right. So it happens. When you travel into space, you go forward into time. Yes,
when you're flying in an airplane, you technically are too. Not on that scale, but
right. Yeah, that's measured. Then it would be in picoseconds, nanoseconds,
and that's not even worth measuring.
Yeah. So it's questionable whether it has any practical observability.
But that's bizarre that it's actually happening.
Yes, it's actually happening because time is not a constant. Time depends on where you are and how fast you're going.
That's awesome.
Yeah.
Well, we only have a couple more minutes left, and I kind of want to touch on this so-called twin paradox. And
okay,
can you sum that up in like 2 minutes?
Okay, I'll just leave a cliffhanger. Just leave you thinking. Okay, you have a situation where you have twins, one on Earth, one in a
gargantuan.
Well, no, we're going to talk just high-speed
okay.
Spaceship, right?
Okay.
So, the observer on Earth looks out and sees his speeding twin and observes that the clock, the atomic clock, is running slower for the twin. Okay?
Okay.
Now, what if you turn the tables? What if the twin, who's in the speeding spacecraft, looks over to the Earth, and to him, the Earth is speeding by? He's stationary in his nice little space capsule, but the Earth is speeding by. It's all relative, right? It's all relative to who's observing.
Right.
So, why is it that time dilation only occurs to the twin who's in the speeding aircraft? It does not occur to the person on Earth. Although you look out, sure enough, he's speeding by. Okay, there's your cliffhanger. Answer that question.
I can't. You lost me, man.
I'm just going to leave it right there.
You lost me. Well, people, if you have the answer to that,
Leave us a comment.
Yeah, go to stdtime.com and leave us a comment. Subscribe to this podcast, first of all, and leave us a comment on iTunes, Google Play Store, YouTube. You can email us at stdtime.com. We are powered by Standard Time. It's a time tracking app and so much more. There's more about that on the website.
Yeah.
And let us know what you think about this whole time travel thing. And we know Interstellar blew it, but I mean, there's some thread
they were
of
really good.
It was a good show. I enjoyed it, and a lot of my theories on hauntings and stuff like that were addressed in that movie. Where I was like, yes. So, but we won't go into that because you think I'm a freak or something.
Right.
But
never listen again.
Yeah, you'll never listen again. So that's all the time we have for today. Remember to subscribe to our podcast, leave comments, subjects that you want us to cover. And if you have email questions, head over to the website, stdtime.com. And we'll catch you next time. See ya.